Hello, and welcome to lecture 15. So in the previous lecture, we learned about the derivatives of logarithmic functions log to the base b of x by thinking of them as they are the inverse of the exponential functions b to the x, and using implicit differentiation to actually solve and find what these derivatives are. Now we're going to do the same procedure and find the derivatives of some inverse trigonometric functions. So we'll start with inverse sine. So firstly, let's talk about what inverse sine means. So we know what the graph of sine looks like. So this is the graph from minus pi over 2 to pi over 2. And if we considered it over any longer range, then it would no longer satisfy the horizontal line test. It would no longer be meaningful to define an inverse, because for any y, well, there will exist y between minus 1 and 1, for which there are multiple x that hit that y. So we have no way to define an inverse unless we restrict some range, just as we talked about when we discussed what arctan means. Okay, so this is sine, and we're going to invert it on this range, and on this range it takes minus pi over 2 to pi over 2 to minus 1 to 1. So change pens. What is arc sine going to do? It's going to send the range minus 1 to 1 to minus pi over 2 to pi over 2, and its graph is going to look somewhat like this. Minus 1 to 1, and it's kind of going to look like this, where this is minus pi over 2, and this is pi over 2. Okay, just so we know what we're talking about, we have some impression. All right, cool. So that is our guy, and now we're going to try and find its derivative. And our procedure is as follows. Instead of writing arc sine all the time, which is length u, we're just going to simplify notation by writing y of x is arc sine of x. And I misspelled it already. Let's do that properly. Okay, so the defining property of arc sine is that it's the inverse of sine. So we're going to write this. Sine of y of x is equal to x. Right? Now, we want to try and find the derivative of y. Right? So the natural thing is to differentiate this equation, which we are now comfortable with. It's just implicit differentiation. So the outer function is sine, the inner function is y prime. We differentiate. So the derivative of the outer function applied to the inner function, we're just using the chain rule, gives us this, and then we get this on the right-hand side. We're going to solve for y, and we get this expression, where y of x is arc sine. And this is indeed an answer, but it's not a very neat answer, right? And what we'd like to do is to come up with a neater answer that doesn't involve arc sine and cosine. Let's see if we can simplify this. And what we're about to do is a very common trick. It's something that is very useful. It seems to come up quite a bit, so it's worth getting comfortable with this procedure. And this is what we're going to do. We're going to look at the defining equation that we started off with, which is this guy. Okay, and we're going to try and represent this equation with a triangle. So let's draw a triangle, a right-angled triangle. Obviously, the angle is y of x, because we're applying sine to it, right? So this is y of x right here. And let's represent the rest of this. So sine, as we know, is the opposite over the hypotenuse. X we're going to think of as x over 1, right? And if we think of it this way, then the natural way to represent this thing with this triangle is to have the opposite side be x and the hypotenuse be 1. Right? This has got length 1, and this has got length x. Yeah, because if we do this, then sine of y of x is opposite of a hypotenuse, which is x over 1, which is x, which is this. Cool. Once we've done that, then we're very happy because we can figure out everything about a right-angled triangle if we know just two of the sides, just by Pythagoras. So look, if we set this to be b, then by Pythagoras, we know that b squared plus x squared is equal to 1. Solve for b. And we have that b is the square root of 1 minus x squared because we want the positive solution. So this quantity right here is just the square root of 1 minus x squared. Yeah? And that makes us very happy because we have that y prime of x is 1 over cosine of y, but now we can read off what cosine of y is, right? Because cosine of y is just the adjacent side divided by the hypotenuse, right? So sine of y of x is the adjacent side divided by hypotenuse, which is just this thing. And then we can put it directly into this formula. So y prime of x equals 1 over the square root of 1 minus x squared, i.e. we have our answer. d by dx of arc sine x is equal to 1 over the square root of 1 minus x squared. That's it. Okay. So that's one of these guys. Let's do another. Okay, let's do another. So let's consider tan. So do exactly the same procedure. So we're going to let y of x be arctan of x. So the defining property is that tan of y of x equals x. We're looking for y prime, so the natural thing is to differentiate. We're differentiating it. The chain rule, the outer function is tan, so the derivative is sec squared times the derivative of the inner function. So we're going to have sec squared y of x, y prime of x is equal to 1. Solve for y prime. We get this. Yeah. And sec is just 1 over cosine. So this thing is just cosine squared y of x, and that's it. Okay. And now we're going to draw a triangle to represent this. Again, y of x is the angle. And what is tan? Tan is the opposite divided by the adjacent, right? So this here is our defining equation. Yeah. So to represent this as a triangle, we're going to take the opposite side to be x and the adjacent side to be 1. And then by Pythagoras, the hypotenuse is 1 plus x squared. So cosine of y of x is just the adjacent divided by the hypotenuse. It's 1 over square root of 1 plus x squared. And the actual thing we're looking for, which is the derivative of arctan, is cosine squared. So finally we have that the derivative of arctan x is 1 over 1 plus x squared. Okay. There is another that we need to know. And that is the derivative of arc cosine, and exactly the same procedure gives you this answer, and it is minus 1 over square root of 1 minus x squared. A really good thing for you people to do is to watch all of this, then shut your notes, then write down this fact, and and just working with what you've understood from this explanation, figure it out and follow exactly the same procedure. So we just let y of x be, this is just to make the notation less lengthy. There's nothing deep about this. And then the defining equation is sin y of x equals x, and then differentiate, then draw a triangle and unwrap your answer with the triangle. Okay? And if you do that, you'll get this. So we have found out the derivative of 3 inverse trig functions, this guy, this guy, and our original guy, this guy. Okay, and at minimum, you'll need to know these. You can expect to have questions involving arc cosine, arc tan, arc sine, where they, in the midterm or the final or in the homeworks, you will simply need to know this. The way to do this is to work this out. Simply work this out, get this right. It's a good practice. It's a valuable exercise in itself. Work it out and you'll get this right. And you won't have any anxiety about this. You won't have any doubt about this. You will be fine. Okay. So with this stuff, then we can just answer some questions. So this is essentially what we need to know for this sections. There are also inverse trigs of all the other trig functions. So we're going to have arc sec, arc cosecant, arc cot, but they are less common. Historically, if you're asked something which involves these, you'll be given the derivative. But even if you're not, if you can do this stuff, you can work out the derivative very easily. Okay? So these are the main 3 I think you should expect to be asked about, and work them out, be confident about them, and that'll be the way to do it. All right, once we have them, then we can do some just exercises to solidify our understanding somewhat. So let's just do one, because once we have them, it is just applying stuff we already know. So this is example 9. Let's put it over here. We have this exercise, find y prime x where y prime, or where y of x, and where I have 2 cases, we have a and b. Let me write that. Where a y of x is down here. Okay, let's be more efficient. A y of x equals 1 over sine to the minus 1. This means arc sine, okay? And the second case is b, where f of x is equal to x arctan of square root of x. Okay. Okay. Let's just do them. All right. Solution. All right, for the first one, it's I'm going to apply the chain rule. The outer function is 1 over x. The inner function is arc sine, right? So differentiate the outer function. I'm going to have minus 1 over x squared. Apply that to the inner function. So we have minus 1 over sine to the minus 1 of x squared. And then we differentiate the inner function, which is this thing, which is the guy we just learned about. It's up here. So then that's multiplied by 1 over square root of 1 minus x squared. Clean that up a little bit. So that's equal to 1 or minus 1 over sine to the minus 1 of x times the square root of 1 minus x squared. And that's it. Oh, I missed the squared right here. Okay, so just stuff we've done before, except now we have to also differentiate arc sine. Okay, let's do b. B is slightly harder. We have this guy. I'm going to use the product rule. So f prime, differentiate the first guy, leave the second guy alone. That part's easy. Okay, leave the first guy alone, differentiate the second guy. Now we've got a chain rule because the outer function is arctan and the inner function is square root of x. So we've learned that the derivative of arctan is 1 over 1 plus x squared, but we're applying it to square root of x. So that's going to give us 1 over 1 plus square root of x squared, which is just x. Okay, and then we differentiate this guy, which will give us 1 over 2 x to the minus 1 over 2. Okay, clean that up a little bit, and that gives us arctan square root of x and plus. So this x to the minus a half and this x to the power 1 and multiply together. So we're just going to have square root of x on the top here, and here we're going to have 2 of 1 plus x. And that's it. Okay, so it is just applying stuff we've done before, things we know well how to do, but now we have these inverse trig functions in the mix. But if you're confident about what their derivatives are, that's really all you need. All right, so that's kind of it for this section. My fear is that because we're in the time of pandemic and online proctored exams with the cheat sheet, some of you are going, yeah, whatever, I'm just going to write this on the cheat sheet. And that's true for this semester, but it probably isn't going to be true for next semester, or it might well not be true for next semester, and it won't be true going forward when you do other calculus courses, multivariable calculus and so on. And it won't be true for your general mathematical development. So resist the urge to just memorize. And I keep saying memorization is not the skill we want to apply here. Memorization is almost people with too good a memories have a disadvantage because they're very tempted to just memorize everything. So do not memorize this, work it out, be confident about it, and that's the way to learn this. And you'll find that even if this explanation seems a bit fast, a bit hard, you will get very comfortable with this. Once you work it out for yourself, you will feel that this is very easy and very natural, and your confidence with all of this stuff will grow. Aside from everything else, if you can work this stuff out, you will feel just confident and comfortable with this stuff, and that's one of the things you want as it builds and builds and builds and builds. You don't want to be memorizing things that you don't really understand. All right, so I'm going to raise the board, and then we'll move on to another topic. Okay, the next topic is one I particularly like because it starts to show you the power of the machinery that we've been developing, and it's related rates. So, as I said in the introductory video, calculus is the mathematics of change, and there are many real-world scenarios where you want to understand the way something is changing, given the information about the way something related to it is changing. And with our language, with our machine of calculus, we can do this in a very efficient way and answer questions that if we tried to do this just with natural language and just thinking very carefully, we'd struggle very, very much. This is part of a general phenomena that if you learn to use this language to quantify questions that you're trying to answer, if you can express the question that you're interested in this language and express the answer you're looking for, then you are in a very strong position because the tools that we have will often allow you to calculate precisely what the answer will be. And that gives you a level of precision, a level of power that extremely intelligent people who don't have this tool can't do. They can't come close to this. So I'll show you what I mean with the first example. So, example. So this sounds a little bit like it's a kind of contrived example, but it isn't so completely contrived. So this is our example. A spherical balloon has air pumped into it at a rate of 100 cubic centimeters per second. And what we want to know is at what rate is the radius increasing when the diameter is 50 centimeters. Okay, let's draw a picture to clarify this situation. So this is our spherical balloon. Air is being pumped into it, okay? As air is pumped into it, its radius has to increase, right, if it remains spherical. And our question is, at what rate is the radius increasing when the diameter is 50 centimeters? So we can imagine that this is not entirely fantastical, because you could be in charge of designing some industrial process that's blowing up a spherical balloon with air, and the tolerance of the rubber used is such that it can only take a certain level of expansion. If it expands beyond a certain rate, it just rips apart. So you might want to know what the rate of expansion of the radius is at a particular point in time. You can imagine being asked this question, and it might seem like a very difficult question, but it isn't for us, because we have the correct, not the correct, but yes, the correct. We have the powerful tool, the powerful tools that we've been learning. We have this language, we have this machinery that allows us to analyze this. And our first step is to rewrite this question and rewrite the information given in the language of maths. So, we write info and question in the language of maths. Okay, so let's start by trying to figure out what is involved in this. So the quantity is described here. So the balloon has got air pumped into it, okay? So the quantity that is relevant will be the volume of the spherical balloon, because that is changing as air is being pumped in, and we know at what rate it's changing because that's given to us in the information, right? So as time changes, this thing is increasing, and we know exactly at the rate because it's being pumped in at a rate of 100 cubic centimeters per second. So every second, we have another 100 cubic centimeters being pumped into this balloon. Its radius is increasing, and we know the rate. Start again. Its volume is increasing, and we know the rate, right? So volume is the first piece of information, or at least the first quantity we see that we have to express in language of maths. And if we keep reading, at what rate is the radius increasing when the diameter is 50 centimeters? Well, the diameter is just 2 times the radius. So this second line is all about the radius, right? So the two obvious things, quantities we have to introduce here in order to describe it in language of maths will be the volume and the radius. And these things in the information are given in terms of time, right? Because this is saying how much the volume is increasing with respect to rate of change with respect to time, right? Because it's 100 cubic centimeters per second. And this thing is what rate is it increasing when? When is time? When the diameter is 50 centimeters. So this is all about time, how things are changing with respect to time. And we are given some information about how the radius is changing with respect to time, and we are asked some information about the way, start again. We are given some information about how the volume is changing with respect to time, and we are asked some question about how the radius is changing with respect to time. Okay, so on our diagram, let us put r of t for the radius, and let's let v of t be the volume at a certain time. Right? Cool. Now, we're going to re-express what we have here in the language of math. So first, we're going to re-express the info. So info. Spherical balloon has air pumped into it at a rate of 100 cubic centimeters per second, right? So the volume is increasing, and we know the volume is increasing at exactly this rate, right? And this is given in terms of rate of change with respect to time. So the way to express this is v prime of t is equal to 100. And it says, obviously, if we keep pumping air into a balloon, it eventually explodes. But that's just information. Until that happens, this thing is holding true. So we're going to write for all t. Okay. Now the question is about the radius, right? And what rate is the radius increasing? What rate of change does it have? Okay? When the diameter is 50 centimeters. So that thing is asking us what is r prime of t. Let me phrase that as a sentence. What is r prime of t when r of t, so the diameter is 50, that will be when the radius is 25. Cool. And look how neat and efficient this is. We have expressed the information in a very concise, precise, neat way. And we've expressed the question in, again, a very concise and precise, neat way. And now we can start to make progress with this, right? It was very obscure, written in the language of maths. Now we can feel more confident because we see that we have this quantity v of t that we have information about. We have this quantity r of t that we want to find out about, right? And the only way this would be possible is if there would be a relationship between the volume and the radius, which of course there is because it's a spherical ball. So if this was just in the plane, right, and we just had a solid two-dimensional ball, the relationship between the radius and the area would just be pi r squared, right, which you all know. In 3 dimensions, probably you don't know the formula. Later in Calc 2, we'll show you how to get the formula out of the methods for calculating volumes that we'll show you then. But in this question like this, you would just be given it. So, true fact. Volume of spherical ball of radius r is 4 pi over 3 r to the power 3. So the r to the power 3 should seem natural. If we're doing things in 3 dimensions, then the volume should increase with respect to r to the 3, right? And it just happens that this is the right constant, 4 pi over 3. Okay, so this is a true fact that if you were facing this question, you'd be given this. Okay? So, in our situation here, we are going to now relate the question to the info. So, question to information. And in this case, it's easy to do because we have the general fact. So for any time, the volume of our spherical balloon is 4 pi over 3 of r of t to the power 3. Yeah? Cool. And now things look good, because what is the question about? The question is about r prime of t at a certain time. The information is about v prime of t. Yeah? And we have this exact equation which is holding for all time. So the natural step now is just to differentiate. Yeah? So equation. Yeah. What happens when we do that? We get v prime of t is equal to 4 pi r of t squared r prime of t, just applying the chain rule. Right? Cool. Now, we are interested in the moment in time when r of t is 25, right? But we know v prime is always equal to 100, so for any t, while the balloon is not exploded, you can just put in 100 here. We have 100 equals 4 pi r of t squared times r prime of t. And at the moment in time we're actually interested in, when r of t is 25, we just put it directly in, right? We have 100 was 4 pi, and then we're going to have 25 squared. R prime of t. And let's simplify that. So 4 times 25 is 100, so we can write that as 100 pi times 25 r prime of t. Divide both sides by 100 pi 25. We have, so r prime of t is equal to 1 over 25 pi. And that's it. When only true at this particular moment when r of t is equal to 25. And this exactly answers our question. So the rate at which the radius is increasing is 1 over 25 pi centimeters per second. Yeah? Cool. So we will do a variety of questions like this, increasing intricacy and sophistication. This is one of the simplest examples we can do. But it is very illustrative of the power of what we did, because after we framed this in the language of maths, the calculation was rather easy, right? Yeah? And indeed, taking some situation which is written in the language of words, written in the language of words, is a real world situation, and then transferring information into the language of maths, transferring the question in the language of maths, this is an important skill. This is something you, as most of your engineers, would gain enormous profit from being able to do, because you will be faced with real world situations that someone will explain to you in the language of words, and then they will often be completely stuck as to how to solve this, how to answer their question. But if you learned your math well, got profit out of your degree, learned the content of your study well, you will be able to do this. You will say, okay, I can express this question in language of math, I can express the information, and then using the relationships between these quantities that will probably exist if there is a way to solve the problem, I can therefore answer the question. And people who are really smart, who don't have these tools, can't do that. They will think you are an incredible genius for being able to answer this question precisely, but all you're doing is using basic math. You know? So I talk a lot about how the concepts are important, much more important than learning the algorithms, even though we're going to test your ability to learn algorithms. And this is kind of an example. The actual algorithm we do, the calculation of the derivative, the application of the chain rule, pretty easy, right? But this part here, transferring language of words into the language of math, this is the new thing, and this is the important thing. This is the thing that computers can't do at all. Right? And this is the part, this is the kind of thing where you should really care about and really try to be good at. In the introductory video, I talked about how if you have math, you have this set of X-ray goggles that give you an extra layer of information, which gives you power. And this is what I mean. This is power. And this is kind of the stuff you can use in your actual life, that I use in my actual life. If there is some question where I have to make some sort of decision, if I'm trying to choose a mortgage, if I'm trying to choose a student loan, depending on how long I study and what my career will be afterwards and what my wage will be, I can quantify these things. I can quantify these questions, and then I can see what will happen given these various choices. And that's a way better thing to be able to do than simply make a guess based on gut instinct. You can certainly make a guess on gut instinct if you want to, but better to have a full picture because you can quantify and make these calculations. Right? So it's not only useful in your potential career, it's just powerful in your life. This is like the next stage above numeracy. Numeracy, you can just add up things, count things. This allows you to, this kind of thing allows you to express your problems and then solve them. We'll see quite a number of these. This is one of the reasons I particularly like this section, and I hope that even if you don't see so far the point of calculus, you'll start to see it given what we can do here and in the later examples I'll show you coming up.